of airless bodies in the solar system.
Okay, thank you very much. Good morning, everyone, and thank you again to the organisers for giving me the opportunity to speak today. This is an attempt at an overview talk, though I've used a lot of our own data in it at points simply because I knew where to get the data from quickly, and so there's a bit of observational bias, as it were, in there. But I'm really speaking on behalf of a large number of people who have worked on this, plus all the luminaries who've gone before me, and I'll mention those as I'm going along. In particular, I'd like to call out Kerry Donaldson-Hanna, who's fortunately not here today, and Ian Thomas, because they've generated a lot of the spectra that I'm going to show for, say, meteorites and lunar samples. And I've included my stock picture of the moon that I took with a small telescope in my front garden many years ago, sort of to remind you of the sort of context of where we started from and a lot of the work I'm going to talk about. But also, of course, it links into some of the discussions from earlier this morning with Paul Hay. So I thought I'd start with the conclusions, then try and justify them as I was going along. And first of all, I'm going to limit the discussion to thermal IR spectroscopy, because otherwise I'd be here for a very long time, and people who are coming after me are going to talk a little bit more about some of the applications and different types of measurement techniques. But also importantly, based on Josh's talk yesterday, it's worth mentioning that I'm really going to talk about kind of what I would consider lightly packed, but also what you guys would consider densely packed media. So this is going to be full of discussions about Christiansen features, Rastral bands and stuff along those lines. I haven't included any discussion about individual grain measurements and the sort of very, very optically thin cases that we talked about yesterday. I'm talking about optically thick. The reason for that is because we're not measuring them, and particularly at the moment, there aren't many people doing that, but it's certainly a very interesting area that we need to look at. And that's one of the things I've really taken away from this meeting. It's been very useful for me. So really what we're trying to say is that the thermal infrared does contain important diagnostic information on the composition, that's kind of a given, but also on the regolith texture. I'll show you some laboratory data that shows this quite nicely. We of course need reliable laboratory data for remote sensing spectra, but in the thermal infrared in particular, you're really sensitive to all these concepts such as packing, grain size, the environment you're measuring them in, and the composition as well. And this is really something that came out both from Josh's talk and other talks that have been given over the last few days for asteroids, and it's really important also for the moon. But we're getting pretty good at this now, and quantifying these effects is accessible to detailed laboratory investigation. So let's look at some fine particulate spectra that have been measured. These are from Kerry Donaldson-Hanna's work, again in my lab, but essentially this is really just sort of picking out what happens when you have small silicate minerals at very small grain sizes. And the important thing to note here is I'm really limiting the discussion to 1600 to 400 wave numbers. I use wave numbers because we use FTIR, so that's kind of up to about 25 microns or 20 microns or so. And in this particular spectral region, you've got this hump, which is very characteristic for silicate mineralogy, called the Christiansen feature. You've got the Rastral bands, which are really driven by the kind of vibrational silicon-oxygen modes. And then you've got the transparency feature, which is a minimum in reflectance. And the interesting thing is that because these are fine particulate spectra, they look quite different to the sort of things that you'd get if you went into, say, the Arizona State University Thermal Emission Library, because they've got these interesting roll-offs and suppressions in Rastral band depths and stuff like that compared to the stronger, to the larger size fractions, for the reasons that were discussed yesterday in terms of volume scattering versus surface scattering. Things like that. But the interesting thing is that they have broad compositional information. So they have composition shifts the positions of these features around. Potentially simpler to derive composition because in theory, if everything's happening very close to the surface, you don't have much scattering going on, then you can imagine everything adding together linearly. So it makes unmixing the spectrum more straightforward if you've got spectra that look a bit like this, but have bigger size fractions, or you put the smaller size fractions in as a part of the unmixing process. This means that you can get a mineral abundance estimate. So this is something been done very well for Mars, but it's going to be interesting when we get to something like Bennu with OSIRIS-REx and asteroids and seeing how that pans out, because we don't really know what the surface texture is going to be like there. But as I mentioned before, these characteristic changes and spectral shapes and everything get pushed around by the environment and by the size of the particle. Okay, so how do we actually do this in the lab? Well, for most of us, as I've already alluded to by my use of spectral unit, we usually use Fourier transform spectrometers. And we've all got, in our various laboratories, we have instruments a bit like this. This is just a Brooker device. There are ones by Thermo and other manufacturers are available, but this is one we happen to have. And the reason we like Fourier transform spectrometers is because they give you fast acquisition of spectra. You can get a very broad spectral range. In this instrument in particular, they do a nice beam splitter that will get you from 2 to 200 microns or more or less in a single shot for a spectrum. You can improve your signal to noise by co-adding lots of interferograms together. And your wavelength range is really only limited by the beam splitter and the detector that you plug into it, because everything else is all reflective optics. So this means that you've got a very flexible instrument for doing all kinds of different wavelength ranges. So most people, most of the spectra, laboratory spectra I'm going to talk about today, will have been measured by a Fourier transform spectrometer of this, something a bit like this. So how do we go about measuring spectral emissivity of minerals? Now, in the thermal infrared, we're usually measuring thermal emission from an airless body's surface. And there are two sort of popular approaches and methods for doing this. One is that you can measure a sample in kind of diffuse reflectance and hope that you can assume Kirchhoff's law applies. Now, that sounds like a very weird statement to make. Kirchhoff's law should probably apply, otherwise, you know, like the thermodynamic arrow of time might be wrong or something like that. But what we mean here is essentially that the sample is isothermal. So you don't have any temperature gradient, so you can assume that you're just looking at the top surface, more or less, of the sample, or it's certainly everything is the same temperature with depth, and that may not be true for an airless body. The advantage here is that it's a relatively quick technique, and it's a comparatively simple setup. You can just sort of put a system together and measure it quite quickly and quite accurately. The other option is to measure a sample in thermal emission, to actually heat the sample up and make sure your radiometric calibration of your whole spectrometer and sample setup is accurate enough to give you a decent emissivity spectrum. And we've already seen from some of the spectra that were shown yesterday that the emissivity ranges, especially for airless bodies and the moon, can be very compressed. It can be within, say, an emissivity of 1 to 0.9 or 0.95. So you need to get this right, this radiometric accuracy, otherwise you can have real serious problems. Of course, this is the only option if you want to start messing around with environmental conditions. But let's think about both approaches in turn before discussing where they work or where they don't work. So the simplest and cheapest and quickest way of doing this is just simply go to a manufacturer of spectrometer accessories, like someone like SpecAc or someone like that, and say, I would like to measure diffuse reflectance spectra of mineral particles, mineral samples, which are small particulate size. And they will sell you something like this. This is what's often called a drifts or diffuse reflectance for Fourier transform spectrometry jig. It's essentially two ellipsoidal reflectors and a bunch of mirrors that play the beam, sort of spread the beam from the spectrometer out onto it goes in the sample compartment of the spectrometer, and it spreads the beam out, so it sort of hits it at a grazing angle, the sample cup, and the sample cups are here, and then this comes down and puts ellipsoidal reflectors, which then collect the light and pass that into the detector module, which picks up the interferogram. So the light comes in, gets splayed over the sample, diffusely reflected, picked up by the ellipsoidal reflectors, and then shoved onto the detector to record the interferogram. People often measure the mixed samples up with potassium bromide powder, and this isn't just for the kind of porosity stuff that you've heard about from the Vanazzi et al. Type work. It's also because you want to improve your signal to noise actually performance. You don't want to saturate some of your bands. And then you measure it relative to either a gold target, which you've had calibrated by a national standards lab or equivalent, or just potassium bromide powder, and you apply scaling because potassium bromide has no spectral features to speak of really in it. And that kind of works, but has some serious deficiencies, which I'll explain in a minute. The other method, which is really kind of pioneered by people like Jack Salisbury at USGS and then Johns Hopkins University, and has been used by lots of other people subsequently, is to, rather than sort of worrying about preferential scattering of angles, which happens in the ellipsoidal or biconical reflection setups, where you can get polarization effects. I mean, if I go back quickly, I'm skipping on. Go back here, you can see some pretty seriously fast mirrors going on here, and that will have orientation effects in your spectra. So the other option is to stick your sample up against an aperture in a gold diffuse integrating sphere, and then measure the diffuse reflection that's coming off of the sample, and then collect a small slither of that energy from the 2π geometry. And you have these guys, this is from Pecker et al. And sensors, I think, but this is a pretty standard setup. You have your detectors on the sides of it, they're plugged in, and then you pick up the diffusely reflected radiation. And if you put a little motorized flip mirror in here, you can then do a bit of self-calibration internally by looking at the diffuse sides of the wall of the integrating sphere. Now, this provides a pretty good direct emissivity estimate from reflectance data, so long as you can assume that emissivity is equal to 1 minus reflection, which is not always true. It's in use, still in use. A lot of people do this, and it complements direct methods of other methods of emissivity quite nicely. The other way you can do it is to heat the sample up and measure the emission from the sample directly. So both the previous methods have used the internal hot source in the spectrometer as their temperature, as their thermal source that they then redirect the light around and look at reflection. The other option, which may seem like the most obvious way of doing it, but is actually quite complicated for a whole bunch of calibration reasons, is to simply heat the sample up external to the spectrometer, collect the radiation with a parabolic mirror or equivalent, then pass the light as the source from the samples, using the sample as the source through the spectrometer and onto the detector. And this is nice because it's as sort of close as you can get in the lab, sort of, to the way that you would do these measurements from space. But it has complications because you have to worry about all the different flux terms that are contributing to the signal the spectrometer sees. So because this is then modulated by the interferometer, all the flux terms that you see in here, so for example, the downwelling radiance term from the environment that the sample is sitting in, any reflections off the sample, that kind of stuff, will get passed through into the spectrometer. So you need a really good radiometric calibration to make sure this works effectively and gives you stable answers. So it's quite a while to get this right, but this is the sort of stuff that Christensen and co have been doing for a large number of years at Arizona State University. They've kind of perfected the way that you do this for ambient samples anyway. And you control the thermal environment very accurately by having a shield, thermal shield, temperature controlled shield around it to calculate out the downwelling radiance, and also they calculate the instrument response function using 2 temperature black body targets of known emissivity that you replace with the sample. So you continuously calculate and calibrate. So which method is best? So here's a rather confusing plot from Phil Christensen and Harrison's paper in 1993, where they compared the different techniques. Now, this is slightly confusing because you've got different grain size distributions, but what they're trying to show here is that the spectral shape, which is, of course, the important thing for getting the diagnostic features in the right places, this is for a quartz sample, is essentially preserved between directly measuring the thermal emission and the hemispherical reflectance method. So the integrating sphere method and the direct emission method give you pretty much the same answer. If you start using biconical or ellipsoidal reflectors like in diffuse reflectance jigs, then the problems you start seeing are you start getting distortion in some of the edges of the spectral bands. This is due to sort of polarization, orientation effects and stuff along those lines. There are things you can do to try and minimize that. So you can see here, these two match very nicely in this sort of region, and then it sort of rolls off where the biconical stuff is going on. Measurements are being made, and that's a problem. So realistically, the two best methods, unless you want a quick look at your data to find out rough positions of bands, is to use something like an integrating sphere, or to do it directly and measure the emission directly. So the hemispherical reflectance is good, but we have to assume that 1 minus reflection is equal to emissivity. And that means that you've got limited options for dealing with non-isothermal samples. And of course, when you go to airless bodies such as the moon or an asteroid, they're going to become kind of interesting. And that's what's going to generate quite a lot of interesting spectral weirdness that we have to somehow deal with in our analysis. So our preferred method is definitely to do direct measurement of emissivity, in my opinion. It's because it's closest to the measurement carried out from orbit. There's lots of background from Mars, where people have done it very successfully. But the approach that was taken for places like Mars and the Earth has been really to assume thin sort of like stuck on rocks. So it means that you're looking at much larger particle size. Typically, the size distributions they use in their spectral arrays are greater than 100 microns. And that's good because it means it removes a lot of these small particle effects that I'm going to show you in a second. but it's also bad because it may not be terribly representative of many places that we are interested in for spectra. It might be, it might not, but it depends on whether or not when we get spatially resolved data for OSIRIS-REx, this is going to be one of the first very interesting things we're going to see, I think, in the thermal data. So, what we find actually for airless bodies is that they're potentially challenging in the lab for a number of reasons. First of all, you have the presence of fine particulate regolith. They could be on the moon. This is a really big deal. I've heard the moon referred to as a perfect storm for thermal IR because you've got all these very complicated thermal structure. You've got some thermal gradients going on all over the place. This can give you kind of interesting non-linear spectral mixing effects for different mineral end members when you put them into your spectral libraries and try and unmix the resulting spectra. Complicated thermal structure that Paul Hayne has alluded to already, not only sort of like due to sort of variations in local topography, but also due to the grain structure itself of the moon or the asteroid. Of course, when you talk about asteroids and primitive bodies, all bets are off as to what they're made of, apart from via the meteorite record. So you're expecting complex mixtures, including organics and all kinds of interesting non-mineral phases to be stuck in there. So what I'll do now is I'll use the moon as an extreme example as I'm going along to show you some of the effects that you can get, which we need to consider when we're analysing these data. So here's a good example of how changes in spectral shape due to particle size can affect it. So this is a complicated spectrum of a meteorite called DAG 083. It's a CO3 carbon chondrite. And this was a sample supplied to us by the OSIRIS-REx project for measurement. And essentially, this is measured under ambient, so Earth-like nitrogen gas conditions to make it nice and straightforward. This is not, we haven't done anything weird to the thermal environment. This is just what happens when you look at different particle sizes. So here you can see the red line is where you've got 254.25 micron size fraction, and you've got this kind of flat-ish region here that leads up to a peak in emissivity and then rolls off. And these are the Reststrahlen bands, and the Christiansen feature is sort of suppressed. When you go to the smaller size fractions, you get transparency features starting to appear. You get Reststrahlen bands compared to the Christiansen feature. It starts to get compressed again, and the contrast gets washed out. And you've got this characteristic roll-off. So here you can see this characteristic roll-off at short wave, which is very diagnostic of small particle sizes, and this reduction in spectral contrast. So immediately, if we saw a spectrum like this, when we went to an airless body at moderate resolution, maybe with a spacecraft, then it would tell you instantly that you've got something going on with the particle size fraction. This could be very useful for comparison with, say, thermal model output. The other thing that can happen, of course, is that you've got no air, which is a really interesting effect, because what you end up with, of course, is gardened impact-driven regolith being produced on some of these objects. Certainly on the moon, this is the case. And that means that radiation now starts to dominate because the thermal conductivity is so low in the way the energy gets transported around in the regolith. And that leads to these extreme thermal gradients. So as Paul mentioned earlier, you can get tens to hundreds of Kelvin temperature difference in the top few microns, few hundred microns or few millimeters surface depth. And what that does, it starts pushing the shape of the spectrum around when you measure it. So this is a fine particulate measurement of, I forget what it was now, it's just an example spectrum measured a few years ago in our lab to show this effect. And what you can see is that this 8 micron approximately feature, the Christiansen feature, is this region of very low volume scattering. It's where the refractive index of the mineral is essentially getting close to the refractive index of the material it's sitting in. So it's getting to about 1, and all of a sudden all the scattering gets reduced. So that means you start seeing deeper into the sample. What that then means is that shortwave radiation that can penetrate deeper into the regolith, maybe a few hundred microns to a millimeter or so, warms the subsurface layers, makes them slightly hotter, and then that's the region that we then start to probe. It's a bit like kind of greenhouse effect type thing, but for a rock or mineral powders. And that starts to probe, so that starts giving you more energy. So you end up with an effective emissivity, that should really say effective emissivity, which we normalize to 1 at that point, which is then higher than the rest of the spectrum. And this is again can then start putting some of that contrast between the CF, the Christiansen feature, and the Reststrahlen bands back. But if you don't include this in your calculations or your measurements when you're doing the analysis, you're going to have problems. But again, this is a small size fraction effect. So this is an example of what can happen when you measure these things. So this is a northite sample measured by Kerrigan and Hannah in one of her papers from last year. And what you can see is the effect of measuring the thermal environment as we change it on what happens to the spectrum. So this was work that was seen all the way back to the 1970s. There's been a large number of very luminous people working in the lab spectroscopy area who've looked at these kind of measurements, and in fact we've seen some of these names before when in Josh's talk. But this is an example of it kind of writ large. This is fairly light-colored sample because it's an orthite, it's fairly shiny looking. So you get this big thermal gradient when you move from Earth-like to Moon-like conditions, and you get this shift in the diagnostic feature peak, the silicate diagnostic feature, the Christiansen feature, and then this big change in the spectral contrast. Now, the important thing to notice here is that this is a pure mineral sample. So this is going to have a fairly uniform set of optical constants. There's no real mixtures going on. So that's why we see these big changes. When we actually look at real samples, real Apollo samples, for example, or meteorite samples, we see much more subdued effects, but we do still see this effects sometimes, and I'll get onto that in a bit. So the equipment that we use to do this is we have an environment chamber, and there are a couple of labs all around the world that do this now, and they have a very similar setup. Essentially, you have a cold shield that you cool down with liquid nitrogen. You illuminate the sample from above with a quartz halogen lamp or equivalent to give you some shortwave heating, and then you feed that into your spectrometer. So the spectrometer is kind of attached out to the plane of the picture, and that gives you the kind of lunar environment conditions that we like to see, and we can modulate that and change that for different airless bodies in the solar system. So you can set up the right thermal conditions and see what that does to the spectrum. So here's an example. We're actually looking at Apollo 15 bulk lunar soil sample, and this is the effect of changing from Earth-like environment, the black line, to a lunar-like environment. Again, these are spectra measured by Kerry, and you can see that once you've set up the temperature gradient, it's pretty stable. You get very similar looking spectra, but the key thing is these spectral shifts. But please note, compared to the pure mineral sample, this is actually much more suppressed. We're now looking at changes in emissivity fractions of a percent, a few percent, no more than that. But what about meteorites? So here's a range of meteorites again that were supplied to us by the OSIRIS-REx project. So this is DAG-83 again. This is NWA 5515. So these are CK4s and CO3s of various alterations. And well, this is where it gets kind of interesting, because this is where the composition of the material and the matrix, we think, is starting to play out. So for example, with DAG-83, when we switched from ambient to simulated asteroid environment, so this was again sort of getting to Bennu-like conditions, we did see a spectral shift, and there are strong bands moving around and all that kind of stuff, like we did for the moon. But for NWA 5515, it's much less pronounced. We see much less shift in the positions and strengths of the bands. And the same is true for NWA 502, which is very interesting. It probably has to do with essentially the intimate mixing that's going on, these much more complicated samples. And this is something that requires further investigation, but it's certainly of high interest in missions like OSIRIS-REx, I think. So we have all kinds of interesting questions that come out of this work that we're all busy exploring in our laboratories. So we have things like how do non-mineral phases and matrix affect the shape of the ground up meteorite spectra? How does the sample preparation, loading stuff into the cup things, what happens with fairy castles, say, versus other types of packing? What differences in regolith production mean between, say, the moon, where you've got impact gardening, and asteroids, where you may have thermal stress production techniques, thermal stressing producing the regolith, as well as impact gardening, or maybe other effects we don't know about yet. More importantly, how do you know if you're getting it right? So one of the things that, again, Kerry had been working on was loading our sample cups in different ways and looking at how the spectrum moves around. This was for direct comparison to diviner data. And you can see that we get some differences in spectral contrast between the CF and the Ristranum bands, depending on how we load the cup. But importantly, the CF position doesn't move, which for diviner is the key thing. And we can then go back and compare that to diviner data from, say, looking at the exact site. This is one of the advantages of the moon. It's one of the great fun things we're going to have with something like OSIRIS-REx, is because we will know where we've gone. The other thing that happens, of course, is when you grind up a sample like a meteorite, you don't end up with something that looks like regolith. So what we did was we did some grinding. We ground up some quartz, actually, in this case, and then shoved it through an aerosizer to give us a particle size distribution, and we end up with this kind of interesting grinding law bimodal thing, which doesn't compare well to, say, 15071's precise distribution from the CAP10 website. So this is something else we have to think about. We have to think about how we prepare our samples very carefully to make them realistic, and where is the dominant term in the spectrum coming from. This is something we'd like to study in more detail. So other things are, of course, surface roughness and directional effects. So surface roughness on varying scales can introduce these non-isothermal effects that Josh Banfield's looked at in a lot of detail. Other people here in this room, Paul Hain mentioned it in great detail, talk just before coffee did. That can introduce interesting slopes into the spectrum. Directional emissivity effects, and we have a lab experiment which Chris Warren will talk about, measuring those later. And also, can we actually model these things spectra accurately using optical constants? Can we actually go back and run a forward model effectively and come up with what we get, the spectrum that we measure in the lab? And that's interesting work. You'll see the next couple of talks, which will be given by Sean and Jesse. Space weathering is something I haven't mentioned, and in fact I haven't heard it mentioned much this week at all, which is interesting. Here's some very provisional data for a couple of different Apollo samples showing the effects. This is Apollo 16, a very immature soil and a more mature soil, showing the effects in the thermal infrared that we see for the moon. This is extremely new, so we don't have any good interpretation of what's going on here. You can see that although the CF is maintaining its position roughly, there's a little bit of shift. You do also get some changes in the band strengths, which is interesting, needs further investigation. So just to wrap up, where do you get all this great data from? Where are your local kind of contact points? Well, there are lots of labs that are doing this work. Ourselves, we do this sort of more interesting sort of complex thermal environment stuff. Arizona State University, of course, have been doing this for a large number of years. Our colleagues at DLR Berlin in the Planetary Emissivity Laboratory, they set up a really high temperature work for mercury and then go as high as 700K, which is pretty remarkable and amazing. Sweary, Brown University, of course, have ReLab, and they have a thermal environment chamber there. Stony Brook University has a small environment chamber for doing work. Johns Hopkins and USGS and many more. But the really important thing is that although there are a few people doing this, it's a very complex parameter space, and we've got a lot of work to do. Here are some of the sort of links for people to look at when they look at these talks online. Cookout, where you can go for more information and find more detail. There's lots more of these on resources. And I'll just put my conclusions back up again, which is essentially there is good thermal IR does contain good diagnostic information, gives you information on the regolith texture. We need reliable laboratory data, and we've got to consider a lot of different things when we go to the earliest bodies in the solar system. So thank you very much.
Questions?
Maybe I missed that explanation, but what is the physical reason why the emissivity spectra look different if the grain size gets smaller and smaller? Multiple scattering between the grains. Okay. Can you model this simply? Okay.
Yeah, what about grain shape? And if the lunar samples that we're measuring in the lab get damaged somehow in the process of getting them into the lab, does that affect the spectra at all?
Probably. Certainly there are differences in the spectra and the thermal conductivity between, say, the lunar samples and ground up meteorite or ground up mineral, because obviously the ground up ones are more rounded, and grain morphology does affect the spectral shape. And again, I think this will probably play into maybe Jesse or Sean mentioned some of the modeling work we've done with different shapes. Maybe, but it will affect the shape, but more importantly, it affects the conduction process through the regolith, because you're much more point-like structures. Yeah.
So of all these various competing effects, when we get to asteroids with spacecraft, we can get spatially resolved data, or even actually from the telescopic spectra, which of the effects do you think are going to dominate on asteroid surfaces in terms of making the spectra difficult to interpret?
I would Now let me think. It depends what asteroid you're talking about, obviously, because the albedo is a controlling effect on, say, the depth of the. Some of these effects are very strongly controlled by the visible wavelength light penetration depth. So when you start chucking in carbon and darker materials and non-mineral phases which plug up the pores effectively, then I would think it'd be grain size that would be the big one. So we should see whether or not there's a big shift in grain size shape or something like that. That would be my thought, but it depends. I mean, if you go to someone which has got a fine particulate regolith produced by whatever mechanism, you're going to start seeing the thermal gradient effect dominate again. So, but there's a plot which I didn't include, which shows how these things get pushed around, and I should have done. But effectively, I think the particle size distribution will be one of the big ones, because the spectral libraries that a lot of people would refer to have been measured for Mars or for the Earth, and they're expecting bigger grains.
I have a follow-up here. Typically, the particle size distributions in nature are nasty, such that most of the particles are small, but the bulk of the mass is in the big ones. Is your method sensitive to the small ones?
Yes, and we've just got a bunch of new lunar samples that we specifically are going to sieve. So we can take the sample as bulk, measure it, sieve it down, measure it, sieve it down, and measure it to see where the bulk of the spectral signature is coming from. Is it clinging fines effect on the actual particles? Is it you're seeing emission from the smallest particle size fraction? What's controlling these sort of gradient effects? Where do things move around? Because a big chunk of something will start to remove the thermal gradient, but you've still got the spectral shape from all different scattering properties going on from the individual small grains. So this is what we're doing next.
I think that's very important.
Yeah.
Thanks.
Yeah.
Great, thanks. Okay, our next talk, we're going to change the order a little bit, and the two will go together. So 2 10-minute talks, or less than 10-minute talks, and then we'll have questions for those two. So this is the Oxford thermal emissivity for regolith model. We have model tests and improvements, comparison with laboratory measurements by Sean Lindsay and Jess Arnold.
That was nice and quick. And if you could, so we give me a warning at 8 minutes, and give Jess a warning at 16. We do this during cumulative time. Okay. Trying to set my own timer here. Oh, wow. All right, well, thank you. So I'm going to be talking today about a little bit of modeling work to support what Neil was just talking about, these thermal gradients and what effect they actually have on regolith samples. And since Neil did such a wonderful job of actually motivating why we need such a model, I'm just going to launch right in and talk about what we need a model that's capable of. Well, we need to be capable of representing a regolith surface in the top few millimeters, and it needs to be able to handle fine particulates like on the moon, or larger particulates on an asteroid like Itokawa. It needs to be capable of simulating planetary body environments and laboratory experiments. So this is pretty much, we need to have something that can do both an atmosphere, so in Earth-like conditions, and we need something that can do airless conditions. We need to be able to control the temperature environment. We'd really like a code that would be modular, so that it has lots of room for expansion and lots of options that we can explore. We need to be able to compute the temperature gradients within the regolith and see how strong of an effect those temperature gradients have on the emissivities that we're going to be measuring in the lab. And from remote sensing, we need to be able to also track all the intensity through the regolith and the intensity that's escaping to space. And we also would really like our integration times for such a model to be short enough where we have a hope of possibly inverting it in the future. So the code that we're using was originally developed by Luis Milan, who was at Oxford for a while. And it's gone through a series of improvements. And right now, Jesse and I are the two main people that are bringing this code to the showroom so it'll actually be useful to the community. It has its heritage in Henderson and Joukowsky, 1994 and 1997. except the major difference with our model is it's updated to have a realistic scattering treatment. It's an IDL code, and it's also coupled with a Fortran version of distort, which handles actually the scattering environment. And since we use distort, that also means that the code is going to have to be able to calculate things like single scattering albedo, phase function, and optical depths, which are inputs for distort. And the main outputs are a steady state regolith temperature gradient, and then the intensity escaping the regolith surface determined by that temperature gradient, and finally a mid-infrared emissivity spectrum. So a brief description. I'm not going to be able to go into the details too much due to time limitations, so have good questions ready. It's an n-layer plane parallel model. So each layer is a sample of particulate regolith, and one of the assumptions that we have to make is that the grains are operating independently, which is not necessarily true in a closed packed regolith environment, but it is the best we can do right now. And what it does is it calculates the radiative transfer and the 1D thermal heat diffusion to actually figure out how we're going to be updating and changing the temperature gradient over time. And then, so we fix a temperature at the bottom and the temperature at the top. We can have a illumination from the top by either simulating a lamp on or a lamp off. And basically, distort will track the scattering environment through here. Eventually, we'll use to update, find a temperature gradient, which will then give us the emissivity that's going to be leaving the regolith surface. Sort of a quick workflow and to introduce some of the inputs that we have. So we input the number of layers that distort is going to use. This is typically 100 to 1,000. You have to determine how thick each layer will be. You have to define the environment. Is it an airless environment? What kind of temperatures are you going to be using? What is your input composition? And right now we're limited to a single composition. But that's very useful for comparisons to laboratory measurements that Neil was just talking about. Grain size or grain size distribution. And to answer Paul's question briefly, but not in detail, you can input grain shape information, packing fraction, and then you have to select a time step size. What you do is throw all these inputs in, start with an initial temperature gradient. You use something, and this is where the code is modular. So you can calculate your scattering parameters, the single scattering albedo, your phase functions, your optical depths, using me theory or T matrix. And T matrix allows us to actually do a little bit of grain shape exploration. So that'll give us our visible, near infrared, and mid infrared scattering. And then we can toss that into distort, let that handle the scattering through the regolith, and that will give us our radiative heating component. Simultaneously, we're going to be calculating the non-radiative heating component. This is just a 1D thermal diffusion. No reason to talk about that more. It's been discussed at length here at Thermops. And then we can integrate forward. We can do our time step, calculate a delta T for each one of the layers, and feed that back in, and then we can iterate until some sort of steady state temperature gradient is reached. And this is defined by an exit criterion, which is variable. We use one where there's the maximum change in any layer is less than 5 times 10 to the -5 Kelvin. And then we can use that steady state solution, that temperature gradient, to calculate the outgoing intensity and convert that to emissivity. In the interest of time, I'm going to skip over some of the more computational guts because I actually want to show you some of the initial results of me exploring the effect of the temperature gradient. As you can imagine from the description of the model, we have lots of different knobs that we can play with. And we divide them into kind of 3 different categories. I'll let Jessie, she's going to revisit this, so I'll leave that up to her section because I really want to spend a little bit of time describing some of our initial results, or at least from the modeling side of playing around just in modeling space and temperature gradients. So we basically, for this talk, we're going to consider 3 different environments. Neil was talking about where you have an Earth-like environment where you're going to have basically an isothermal temperature gradient. And then we're going to have lamp on and lamp off. And the depth here is going to about 9 millimeters. And you have the temperature range right here. This is with the lamp off, so you have no solar illumination. You end up with a temperature gradient like so. And whenever you turn that on, Neil was saying that you have the shorter waves that are penetrating deeper into the surface, heating up the subsurface. So you end up with this kink and this very steep temperature gradient here, and then it returns to the isothermal temperature. And the one thing I really want you to take away from this one is the difference between the isothermal, so here in green, and then the 2 where you actually have a temperature gradient. And for the keen eye, I know that the labels are a little small. this is about a delta T of about 230K. And that's just in 9 millimeters, and really much less than that. So that's a very extreme temperature gradient. And you can see what effect that actually has on the spectra here. And then the difference between the lamp on and the lamp off, that's not very different whenever you're considering the Christensen feature, the Restland bands, and your transparency feature. So one of the more interesting ways to actually start investigating the temperature gradient is to actually let the model run and let it run all the way to steady state. And this will actually give us some ideas of how long we actually have to integrate for, and do we have to go all the way to steady state. So with this very dense plot over here, the way that we start with an initial isothermal temperature gradient, then we allow time to just integrate forward, and we're using 1 second time steps. And every 1,000 time steps, I'm outputting the temperature gradient, and I let it evolve all the way until it reaches steady state. So the exit criterion kicks. So you can see that it took about 30,000 time steps to reach that, and that's with 1 second time steps. Unfortunately, that's about 6 hours of runtime, which is not very tractable. But you can see after about 1,000 time steps in this inset here, the location of your Christensen feature doesn't move around very much, and it's pretty, it stays in the same location. The shape of the Restland bands is not changing, but you will see that change in the contrast between the Christensen feature and the Restland bands. If you actually look at kind of the blue-green colors here, and you compare those for the emissivities, you're not seeing very much change in the emissivity. So we can call almost an effective emissivity at about 10,000 time steps, which is a lot faster in runtime than 30,000 time steps. And this is also stable in most setups with a 10-second time step instead of 1 second, which can really speed up the calculations. So this is the same experiment, except we've turned the lamp on. And the one thing I want to point out is that you get this very extremely steep temperature gradient in the top millimeter, and it doesn't take very long for this temperature gradient to be established. And once it's established, doesn't matter how long you integrate to, your emissivities, at least according to the model, lock in, and you see essentially no change. That's indicating that maybe this uppermost steep temperature gradient is one of the most important factors. And this also means that if we're doing simulations with the lamp on, or sort of daytime measurements, then you don't have to integrate very long, so we can do these computations very, very quickly. And finally, I was very interested in that steep temperature gradient and how that might compare to subsurface temperatures. So here I've just varied the bottom temperature in the code over a wide range, and went ahead and let it evolve to, these ones are about 100 or 10,000 time steps. But you can see this steep temperature gradient and even a variation of about 30K. You get that same effect that you end up with emissivities that overlap on top of one another. So the subsurface temperature doesn't matter as much as this very steep uppermost temperature gradient. And with that, that concludes my part of the model, and I'll invite Jesse up here for the other half. It'd probably be best to hold questions for the end, since she will actually probably answer the questions that you have. I'll just move forward there.
All right. So first, I'd like to acknowledge my co-authors, Sean, Lindsay, and Neil Bowles, who you just heard from, and especially Carrie Donaldson-Hannah, because she helped me acquire most of the laboratory spectra I'll actually be showing. Since Neil and Sean have done such a good job, I won't spend too much time on the motivation, but Sean just described the model and some code testing and validation, and now I'm going to go through model validation through environmentally controlled laboratory experiments. So Sean showed this briefly, and I'll also show this briefly. There's a lot of things that we can play with in our OTHER model, and I've just divided it into 3 very rough categories. One is just a parameter that we need to enter into the model that isn't really related to our lab environment or the samples, and Sean showed some plots to do with that. He also showed some things related to the lab environment, which is what I'm going to be focusing on, and I'm also going to be focusing a little bit on the sort of bottom 4 things, especially mineral composition and grain size. Okay, so how do we enter mineral composition into the model? So we put in optical constants for the relevant composition and also heat capacity. And then the sample that we decided on, Carrie had some San Carlos olivine that was available to grind in sieve, which I just pulled a random internet picture that ours looked very similar. So we sorted this in sieve to different size separates, but we've only had a chance to measure the size separates in the bold, so the smallest and the largest, just to give us a rough idea of how our model is doing. Okay, and as has been gone over, I'll be talking about two different sort of laboratory environments. One is the ambient or Earth-like, and the other is the lunar. But in the ambient, unlike Earth, we're not using any solar illumination, and then in the lunar, we will be using solar illumination. So my first couple of plots will relate to how we actually make the thermal gradient in the lab. So that's sample cup temperature and illumination, and comparing our model results to what we actually measure. So over here is our model temperature profile for different sample cup temperatures. And Sean just showed something really similar, but that was for quartz, and this is for olivine. Okay, now comparing the modeled emissivity spectrum here to what we actually measure, we can see that here our sample cup temperatures are going from 272 to 393, and that sort of corresponds to the red in the model plot. And we can see that in both cases in the lab measured, the sample cup temperature doesn't have a huge effect on the emissivity, especially at the Chris-Janssen feature, maybe a little bit in the Ristron bands. All right, the next thing I tested is different lamp settings, which the way that we tune this is a little bit different in the model than in the lab. So in the model, I just took a variety of lamp temperatures that they vary quite a lot, a few hundred Kelvin. And so this is the model temperature gradient here, the modeled emissivity spectrum. And now here's our actual measured lunar environment effective emissivity. And here, though, in the lab, instead of varying the lamp temperature, what we do is we just change the lamp setting until it gives us a certain brightness temperature at a wavelength that's somewhat featureless. So that's probably why there's less variation in our laboratory spectrum than in the modeled, because the modeled, like I said, I decided on quite a large range of lamp temperatures. But even so, for the model, again, the CF doesn't change too much when you change this parameter. And in the lab, even in the Ristron bands, it doesn't seem to matter too much. Okay, so now on to the thing we're sort of interested in, and the sort of things that we want to know about surfaces like grain size and composition. So because we haven't measured the actual particle size distribution of our sample yet, the way that I chose the different particle radii for our model is just based on our sieve sizes. So keep that in mind. And also keep in mind that all of these plots, except for the very end, are for a single grain size, and we haven't really done much with distributions yet. Okay, so this, first I'll show you our modeled ambient emissivity spectra. I have grain sizes going from 1 micron radius to 125 micron radius, so blue to red. And then this is the model temperature profile. And now looking at our measured emissivity spectra for the ambient environment, the blue is a diameter of less than 45. So that sort of corresponds to the range in this plot going from purple to yellow in terms of grain sizes. And then the other size that we've had a chance to measure is the radius less than 125. So that's the red here, and that sort of corresponds to the red modeled spectra here. And so this is kind of nice because we see the change in the depth of the Ristron band. That's good. We see the change in behavior of the shorter wavelength. So we see this sort of roll off that Neil was describing earlier. That's good. And the other neat thing that we're seeing coming out is for the grain sizes is we're modeling the transparency features. All right. Now, okay. Now these are the same. This is the same sizes that I showed earlier, but modeled the vacuum environment. Here we seem to have sort of a less clean story. The neat thing is that we see the effects of the lunar environment. So we see this the Ristron bands getting deeper, especially the smaller grain sizes. So that's blue here and blue here. So that's sort of neat. But we have some sort of odd, unexplained thing, like the behavior of the Christiansen feature is a little odd. So you have, so for the smaller grain sizes, you see this, but then in the intermediate, it shifts and narrows. But then for the much larger grain sizes, it's doing sort of what you'd expect. And at first I thought this might be an issue with our normalization, but it's really hard to see on this plot, but also happening, and maybe you can see in the secondary sea. So that's something we need to explore a little bit more. Okay. And then finally, I sort of noticed that our less than 22 micron spectra looks like the much, much smaller stuff we modeled. So like, it looks very much like the, 1 in 10 mic stuff. So I wanted to see the effect of doing particle size distributions that have different ratios of very fine things to a distribution centered around 20 microns. This is based on the plot that Neil showed earlier of the arrow size data of quartz. So I have a distribution centered around 20 microns, a distribution centered around 0.5, and I varied the ratio of the relative surface areas from 0 to 0.3 for the 0.5 microns. And what's odd to me is that this doesn't seem to change things too much. All right. And this sort of answers the question that Paul was asking earlier about what we found of sensitivity of the modeled emissivity to these various things. And I'll just very briefly say it seems fortunate that the things we care about seem to be the things that the model is the most sensitive to. So that's mineral position and grain size. And grain shape is something we haven't explored very much yet. So I'll just put up our to-do list here. So first thing is to model both get data and model the grain shape and size distribution for maybe adding CDE or create dipole approximation. And as Paul mentioned, this is what we're trying to model. This is the actual lunar regolith grain. This is what we're working with in the lab, which is hand ground phosphorite, but we're modeling it with this. And to me, now here's my YouTube ready moment. That's kind of like trying to understand this by looking at this and modeling it with this. All right. Also on our to-do list, multiple compositions, non-uniform layer thicknesses, trying to understand the effect of the uppermost steep part of the regolith and varying porosity by layer. And so, running out of time. So our question is, how would you like to see this model used?
Question.
So obviously this is really great work. What's disturbing from the remote sensing point of view is that thermal gradient in the upper millimeter. And I mean, we knew this might be an effect, but just seeing how extreme it is kind of sends the message home that we need to be really careful about interpreting infrared emission measurements at any particular wavelength. So have you calculated the weighting functions for example, the donor channels? See if you have that temperature gradient, what brightness temperature would we actually measure for a given composition? I mean, it's kind of captured by your emissivity spectra, but
so that's something we haven't done yet, and that's why, like I said, it's one of the things on our to-do list to sort of understand the effect of that gradient at the, those less than top less than a millimeter. So we haven't quite gotten there yet.
That's an interesting point to try to put together weight functions.
Yeah.
Could you say just a little bit more about the origin of that? I mean, I guess it's that the visible light gets into the soil. It doesn't just get stopped at the surface. But could you say just a little more about why that is?
Are you talking about that first millimeter with
Yes.
the seat temperature? Gradient?
Yes.
And it is a fact. Once you turn the lamp on, since it's shorter wave radiation, it can penetrate deeper into the soil. And it's depositing heat. And as Neil was describing, almost like a little mini greenhouse effect, except in a regular surface. So you end up with all the heat being deposited just subsurface, and then it can scatter about in the layer. But since the heat's being deposited there, it's really driving the temperature where the maximum is going to be subsurface rather than at surface or deeper down.
So the spectra that you both measure and model really well with that really strong Christensen feature, and then kind of a big contrast before you get to the Restrepo bands. We don't from the Spitzer data of asteroids, I don't see a single asteroid spectrum that looks like that.
Well, I think
okay.
yeah, I think Neil mentioned this somewhat. Is that like asteroid and even lunar samples look very different from pure minerals, and we're only looking at a pure mineral right now.
Okay.
So
that was going to be my question. What effect do you think is making that happen? So you think mixing of minerals?
Yeah.
Although to comment a little on that, when you showed all the mid-infrared spectra of S-type asteroids and they were relatively boring, I actually was very surprised and a little worried.
That's true. That's true.
Right.
Uh-huh. Right. 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 Okay. Okay.
All right, last one for Ellen.
Is this on? Just thinking a little bit more about this strong temperature gradient right at the surface. I'm wondering if part of that is that your model is really smooth compared to the scale of the particles. Is there some way to kind of make sort of poke little holes in it, or make the surface rough so that it mimics a little more what a real surface might look like?
Right. So yeah, there's definitely going to be a surface roughness effect, and our model as it is now can't really do that, just because we're using Dysart and me theory. So basically, we can only specify a porosity for a given layer. We can't really, yeah.
Okay, thanks.
Yeah.
Let's move on. Thank you. Next is Tris Warren, Oxford Space Environment. Ganometer, yes. Surface roughness effects on the directional emissivity. Okay, so 8 minutes, and I'll warn you, you have 2 minutes left. Thanks.
Hello. So for those of you who don't know me, I'm Tris, and I'm going to talk today about an infrared goniometer we've been building at Oxford. I'm currently just finished my PhD with Neil Bowles, and there's been a whole host of people who've helped out with this project. I've tried to list them all there. So just to give a quick overview of this talk, I'll start by very quickly talking about our original motivation building the infrared goniometer. Then I'll get into the the nuts and bolts of the design of the goniometer and talk to you about some of the validation work we did for it. Then I have some initial results we've measured using it I'd like to share with you, and some more work we've done to try and model those results. So originally, we were trying to improve Dave Page's diviner thermal model. Talk about how his model works, as we've heard quite a lot about it already today. But basically, the model does a very good job at trying to recreate the lunar surface temperatures. It does a very good job when we're in equilibrium in sunlit areas. If we look at a map form, one of these maps here is model data, and one of these maps is measurements we've made by diviner. As you can see, like for 90% plus of these areas, the model does a very good job. It's statistically the same, and you can't really tell these two maps apart. The problem comes when you get to areas that have complex illumination, like in the coal traps, the talk before the colleague was talking about. So at the poles of the moon, at those areas, the model seems to be predicting too warm temperatures to what we observe with the diviner. That's what this graph here is trying to show. That the model and the data are out at regions for low temperatures. What we think is going on here is we think that there's a surface scattering effects, particularly in thermal infrared, that the model is not taking into account. Currently, the model just assumes isotropic scattering, which is probably incorrect. So I'd just like to quickly define, I'm going to talk a lot now about directional emissivity, so I want to just quickly define what I mean by that. So we have here a solar source and a detector, which is represented by that very creepy eye right there. So directional emissivity is just how thermal infrared radiation is reflected or re-radiated off a surface for all viewing angles, so for all incident emission and scattering angles. And this is very similar to the bidirectional distribution reflectance function in the visible. The only difference is that the directional emissivity is referring to the infrared. Of course, one big difference between the infrared and the visible is that in the infrared, you don't actually need a light source. You can just heat the surface up from below and measure how it emits with varying emission angle. And in that case, we just define our scattering angle from an arbitrary plane. For our experiment, actually, we've started off just making measurements like this, so just heating the sample up from below without a light source. It's just to try and keep the experiment a bit simpler to start with. So this is the design of our goniometer. We have a radiometer carriage. I'll point it there. Sitting on this 180-degree arm, and it moves up and down that arm to change the angle. Sample sits in the center. And then that whole arm sits on this big ring, which can rotate around the sample to change the scattering angle. And like I said, at the moment, we're just heating the sample up from below. But in the designs, we left room for to put in a illumination arm, which we hope to add later in the future. This whole goniometer is designed to fit inside a 1 meter radius vacuum chamber, to give you an idea of the scale of the thing. And then it's all surrounded by a cold shield. We're surrounded by a cold shield for two reasons. One is that we want to reduce the thermal background noise, and the second reason is to set up a like a space-like environment around the sample, so we can induce a thermal gradient in the sample, a powder sample. So this is just some additional details about the goniometer. So the radiometer, we built it to be very flexible, so we can change in detector elements and baffles and filters depending on what we want to do. So if we want to make measurements in the visible, we can do that by putting in an appropriate detector element and filters. Or if we want to make measurements in the thermal infrared, again, we can do that by changing out the detector element. The filters we are using are not coincidentally very similar to the filters on Diviner. because we had spare ones kicking around in the lab. This bottom plot here in the bottom left shows the goniometer sitting inside the vacuum chamber, and the plot on the right, this plot here, that's the cold shield surrounding goniometer. So the lid of the vacuum chamber is up, showing you the cold shield, and in here the cold shield isn't around the vacuum chamber. This is the sample changer here. Currently we have 4 samples in there, and it's designed to have sample cups like this to hold powdered samples. But at the moment we're mainly looking at black painted discs because they're a bit easier to manipulate. So this is the validation work we did. I'm going to skip through this quite quickly. We measured a spectral on target and compared it to a measurement done by a fire goniometer, which is a visible goniometer. And as you can see, the 2 measurements are in good agreement. And then we wanted to do some validation work in the thermal infrared. So we measured a load of infrared LED throw cones, and that worked really well. Actually, this is a measurement we made of this particular LED, and we were comparing it to its datasheet value, which is this inside line here. So it picked up a lot of the similar features shown on the datasheet, which was nice. And then we wanted to make some measurements of some surfaces. So we thought we'd start with something simple. So we started with this black painted disc here, which is just a very smooth, this is Nextel black paint. And we thought we'd start by just making a broadband measurement. So we had a KBR window, so we had lots of signal to work with. And we didn't turn on this isn't under vacuum or with a cold shield on. I naively sort of expected the response of this direction of emissivity of this sample to look like a straight line, like an isotopic sample. So same emissivity no matter what viewing angle you viewed it at. Of course, when I measured it, this is what I measured. Definitely not isotopic, particularly at 45 degrees and above. So I managed to find similar measurements that have been made before by similar setups. And as you can see, there's actually quite a spread in the measurements. I think that's probably due to the slightly different textures of the paint on all the different surfaces. But it's nice to see that fit quite nicely inside all of this spread. So I tried to model this just using a simple Fresnel model. Blue line is the measurements we made, red line is the Fresnel model. And as you can see, it didn't fit very well. There's 2 reasons why this could be. One is that I'm straight through the black paint to the underlying metal below, but I don't think that's likely. I think what's more likely is that I'm seeing some effect due to the surface roughness of this target. And the next slide hopefully shows why I think that. So this blue line is the target I was just showing. Red line is another target I made, which much more texture to it. And you can see again, these 2 have a very different function from 45 degrees onward. It looks like surface roughness has a large impact. So I then tried to take into account this roughness in modeling to try and improve my modeling. And I was using this multi-surface Fresnel model, which basically just takes a set of slopes and then weights the contribution from each slope using a Gaussian distribution. And as you can see, things, but it still wasn't a great fit. So I then switched to a Monte Carlo ray tracing approach, where I just took some code from off the web from this website here. And as you can see, it does a much better job. So I haven't actually had any time to properly fit this. This was just done by eye. And you can see that the data and the model are basically on top of each other now. And the nice thing about this modeling is it includes multiple bouncing, which I wasn't including before in my modeling. So it appears that is quite important. When you're inputting parameters into this ray tracing code, the thing you're trying to do is you're inputting the height, RMS height distribution, and the autocorrelation function, which is the typical distance between 2 features, so between like a hill and a valley. And I was getting values of about 2 microns and 100 microns between the typical features, which is about right for what I think is the surface roughness of this target. So I'll just quickly describe this. This plot here shows you how the multiple bouncing is when it is kicking in, and you can see that it's kicking in from about 40 degrees onwards, which is quite nice because in the plot earlier I was showing where my measurements deviate from a Fresnel-like response is about 40 degrees and onwards. So it looks like multiple bouncing becomes important from then onwards. And this graph here is just showing a 2D slice through the typical surface roughness I'm expecting. So you can see the RMS height distribution is of the order of of the order of a micron, and the typical distance between 2 features is of the order of 100 microns. And that's the concluding slide. So we've got a goniometer which is making directional emissivity measurements. We think that surface roughness is very important, or it looks like surface roughness is very important. And it seems to be important to include multiple bouncing when you're trying to model this. And this little video just shows a scan pattern of the goniometer, so you can see it going around the sample in the center there, making measurements. That's it. Thanks very much.
Couple questions.
I like the fit you did on the directional emissivity. I've done some things like this myself, but indeed the roughness makes it complicated. But the Fresnel model is mathematically, of course, the thing to do. But why do you use a constant n index of refraction? It could vary with wavelength. You're integrating here over a very broad wavelength range, and there could be, of course, a imaginary part to the complex index of refraction, with making it towards a better fit, even without invoking ray tracing and so on.
Yeah, so I'm pretty sure the imaginary part of the refractive index is 0, because the Fresnel law gives a formula for the imaginary part of the refractive index, and if the electrical activity of the material you're looking at is 0, then the imaginary part will be 0, and the electrical conductivity of this paint is very, very small. Yeah. And as for different refractive indexes across different wavelengths, you're right. It probably does change a bit. We need to start doing narrower wavelength filters and see. That's the best we can do.
Josh, okay.
So this is just kind of a little more of a statement of amazement than a question. So in your emissivity, in your emission phase function, you're seeing the effects of roughness at the micron to 100 micron scale. Or is that?
I think I am.
That's a pretty fine scale. So what does that imply for like an emission phase function measurement of an actual surface? What scales will we be most sensitive to?
Well, all I can say is that for this surface here, so the reason I think we're sensitive to down to the micron scale is that this surface deviates from a perfect Fresnel-like response, and it appears that if you fit it with a ray tracing approach, where you give it micron scale, 100 micron scale roughness, then model the you then accurately model what you're measuring. So I guess I haven't directly measured surface roughness, influences of surface roughness at the micron level scale on the directional emissivity, but I'm just implying it. So I guess I need to come up with some kind of experiment where we find something that's smooth on the micron level scale and show that that has a perfect light response. But that's really, that would be tricky. Sorry, that's not a great answer.
Okay, last one.
So you'd expect this session to be polarized, right? How did you deal with polarization, and could you measure the polarization?
So we could, if we put some polarization filters in front of on the radiometer carriage, which would be really great to do. I'd love to do that. At the moment, I just assume that this is 50-50 polarized. It's unpolarized, so I don't. Oh, really? Okay.
If you look at the Fresnel plot, it's different than the plane polarization.
But why would it be? Why would one of the say? I just assume that there's a 50-50 contribution from each Fresnel law, each Fresnel law. Why would it be preferential at one angle?
For the same reason we're polarized, right? The emission is going to be polarized, so then you just have to treat that.
Okay.
Okay, thanks.
Thanks.
Next talk, Marco Delbo. Thermal cracking of surfaces of airless bodies. New experiments.
Okay, thank you very much. So I apologize for those of you that have already seen the book, but there are some new stuff at the very end, so stay tuned. So here I'm going to show that basically rocks at the surface of asteroids breaks because of the thermal temperature excursion between day and night. And these debris from the rock breakup produce regolith. So it's an important, this process, thermal fatigue cracking is an important process for making regolith. And these are the collaborators of this project that has been supported by a grant from the ANR. I don't think I have to describe this, how regolith important is. It's just very important because all the information we get from spectroscopy, polarimetry, thermal IR is coming from regolith. So it's pretty important to understand how regolith develops on asteroid. And this is the classical picture of moon forming regolith that is supposed to be similar on asteroid. Paul really well described it. There's papers by Gold and Hortz and so on. And the idea is that you have here an impact that from an asteroid that basically go through the surface and hits the bare rock and expose new boulders on the surface of the moon. And then these boulders are comminuted by micrometeorite coming down, impact these boulders and breaking them. So the origin of the regolith was supposed to be due only to impacts. It's an impact process. And Friedrich Hortz and collaborator developed in the 70s and updated more recently a Monte Carlo simulation of the residence time of rocks on the moon. And basically, the result of this model, it basically tells you that this is the, I'm sorry, yeah. Bad luck. Good. So you can see here the survival of time of the rock on the moon, on the surface of the moon, is function of the diameter in centimeters. So you say a rock can survive between, let's say, around 10 millions of years in these science range. It really can go from 2 to about 30, 20. So we updated this model to asteroid. Basically, the source of the projectile, so the meteorites, is from the zodiacal cloud. And here you see a picture of this, so a diagram of the zodiacal cloud, a cartoon. Basically, this is the sun, this is the heliocentric distance, and this is the inclination on the above the ecliptic. And because of the pointing, so the dust is mostly produced here by the grinding of comet. This is a model. There are many papers. The one of the David Nasvorny et al. Showed this process, and the model matched pretty well with the observation. So the dust is produced here, and then because of the Poynting-Robertson effect, the dust is spiraling in towards the sun. So the volume abundance of particles increases as you go closer to the sun. So you have more impact here than here. And actually, we have a model. Actually, Alessandro Morbidelli did this calculation for us. He has a model of these zodiacal particles, and we can stick bodies, let's say planets and asteroids, in these zodiacal clouds and calculate how many impacts you get per year, per meter square. And it turns out that there is 10 times more impact here than here because of this Poynting-Robertson effect increasing the density of particles. And so we can actually extrapolate the Hertz model from the moon to near Earth. So the near asteroid gets more or less the same number of impacts than on the moon per year per square meter. The velocity is slightly different, but it's not very different. On the main belt, on the other hand, you have 10 times less impact. So we can say that this is the survival time of rocks on the moon. This will be the survival time of rocks on the main belt asteroid. Here is a 2.5 AU. So it's a pretty slow process. Investigated another process. This cartoon from Earth geology from Madden et al. That shows the idea. So imagine you have a rock here in the morning that is illuminated by the sun. You have the warm part is this is on the east side, and the west side is cold. And this temperature gradient reverses during the day, throughout the day. And so you have a temporal and spatial gradient, a temperature gradient in the rock that causes a differential expansion and contraction of the rock, which leads to stresses, to a load, which causes stresses, mechanical stresses. And this is cyclic effect. And when you have a cyclic stress, you can have what is called the material fatigue. The fatigue is basically a cyclic damage of a progressive damage of a material due to cyclic loading. It is interpreted as a crack growth. So you have micro cracks in any material. Could be a rock, could be a bone of a body, could be a plane, could be a wing of a plane, could be an axis of a motor, and so on and so on. And so this cyclic loading increases pre-existing the length of and the volume of pre-existing cracks. And these effects are known since a long time, and I promise to Paul to show this. And so there is a correlation on it has been shown that there is a correlation of some event due to cracking on the moon with the diurnal phase, diurnal cycle on the moon. And here you see from this paper by Dunbeer and Sutton in '74, you see the events measure the histogram here, measured by Apollo seismic network deployed on the moon as a function of days after sunrise. And you see there's a very good correlation between these little events. It could be cracking of rocks on the moon, or could be landslide due to there's a very good correlation with the diurnal cycle. So the interpretation is that it's probably due to some thermal events. We wanted to understand if this can also happen on asteroid. And so we took, that's why it's in the, this talk is in the laboratory session, because we took samples of carbonaceous chondrite, ordinary chondrite, and put it in the oven, and we basically cycled them with period very similar, temperature very similar to asteroids. And we use CM2 chondrite, Murchison, and LL 3.2 from the Sahara collection. So this is the cycles we did. The blue is the cycle did in the chamber, and the red and the pink are typical cycles of near-Earth asteroids. So it's not too it's not exactly the same, but it's not too different. The thing is that we did only 407 cycles, whereas a rock or like something on the surface of an asteroid can go through billions of cycles. And this is our laboratory experiment protocol. So here is sketch what we did. So before we started the cycling, we actually did the X-ray tomography of our samples to look inside. Then we did a week of cycles. Then we took them out of the chamber with another scan, and then we put them back for almost a month during the summer vacation in France. Then, so we had the chamber, nobody touched it because nobody works. And so we eventually, when we returned from vacation, we took them out and we scanned them again with the scanner, tomographic scanner. And here you see an example. This is just a slice of a tomography, and you see a pre-existing crack on the Murchison, and you see a T0, so before, 1 week after, and 1 month and a week after. So you see that something happened. And we even formed some regolith from the Murchison, not from the other meteorite. The other meteorite is much harder. And so they're like chips that fell off of Murchison due to thermal cycling. So we took great care to make sure that we didn't cause this by handling the meteorites. And we did another experiment where we actually did more or less the same setup, but we didn't activate the thermal temp cycling in the oven. So we did the same setup, but we didn't go through, we let everything at the same temperature. And we didn't scrap growth nor production of debris. So we measure, I don't detail this, but we measure many crack in, well, not many, like 30, okay, thank you, in Sahara and Murchison. And this is the average crack growth after, the average relative crack growth in percent after 400 cycles, which is pretty fast. So if this would continue this way, there will be no, every asteroid will be very, very fine red. But it is known from the theory of thermal fatigue that the crack growth can level, and then when you reach the crack reach a certain length that is close to the length of the object, then you have a catastrophic breakup. So, and we developed a theoretical model that matched. So we put the parameters on thermomechanical parameter in this model. And the model is not fit to the experiment, but we could reproduce some of the crack growth in our experiment. Not perfect, but the model is not fit to the experiments. We took literature data for the thermal and thermomechanical parameters and developed the model, and we compare to the experiment. And so then we use this model to extend the number of cycles to the to the lifetime of asteroids, and we found that, and then we compare the time it takes for a crack to grow through a rock this diameter as function of time. So the left is the red and left is ordinary chondrite, the blue is carbonaceous chondrite, top is at 1 AU, bottom is in the main belt. And as the straight line is the Hortz et al. Time to break objects by micrometeorites. And yet you can see we are not always, but we are kind of faster than the micrometeorite bombardment. Some new experiments. So this is another setup. We use a laser here. The thermal cycling is much faster, but we can even create, well, we probably extend a pre-existing crack. But here in the scanning microscope image of the surface of a slab of emerging stone, and you see nothing at least below the resolution, above the resolution of the instrument. There might be cracks below the resolution of the instrument, which is a couple of microns. After 180 cycles, you perfectly see the net of cracks. And this is Allende, which is a CV3 meteorites. We also crack it. It took much longer. And surprise, we did nothing to this CR2 meteorite. It's also another carbonaceous chondrite, but we could get no cracks at all. And our interpretation is that the CRs have more metal, and so the metal is ductile and absorbs this strain without producing much stress. There's also a new set of experiments that are done at the Johns Hopkins University by the Katie Ramesh group, and here they have heated and cooled a slab of ordinary chondrite of type L, and they measure with the DCI digital image correlator the position of features on the object, and they measure this strain field, and you see how strain field builds up as you increase the temperature, and you see here some effects around the pre-existing crack. There's a strong strain here, and then it goes down. You see very well this strain field around this pre-existing crack, and the measurements show that this crack is actually growing cycle after cycles. And conclude with two implications of this thermal crack. So it could be, but it's not sure, that I mean, we can explain fragmentation much quicker of material on the surface of asteroid much quicker than micrometeorite bombardment. And it's interesting that the exposure age of the regolith Tokawa is very young compared to what would be implied by the micrometeorite model of Hort. There might be other explanation. The thermal cracking is a strong function of the temperature excursion. So if you are an asteroid that is very close to the sun, you crack like crazy. And for example, if we extrapolate our model to an object 3 AU from the sun, basically produce grains very quickly, almost done. And we can say that the radiation pressure can blow these grain away. Object is small enough, as shown by the calculation of Jewett. So basically, we can destroy, erode away object of this 100 meters in a few millions of years if you go very close to the sun. So low perihelion, dark carbonaceous-like asteroid should be gone in a few millions of years. I think I can leave the conclusion here on the screen, and I stop with that. Thank you.
I'll take a project and just ask a quick question.
Yeah.
Did you consider sun-gradient objects which are closer than NEAs?
No, we didn't. We didn't. It could be
Extreme.
Could be dramatic.
Yeah.
Yes.
Okay. Other questions?
Yeah, this is really cool. And I was wondering, is there some kind of feedback between the thermomechanical breakdown process and the micrometeorite? And because you mentioned that having the pre-existing crack helps speed up the process, and maybe the crack itself is started by a micrometeorite impact, but that also changes the conductivity of the material and so on.
Yeah, we haven't considered that, but I like the idea. It's definitely possible. And also, thermal cracking it could be the other way. It could be both ways. Thermal cracking can grow cracks. Sorry, thermal fatigue can grow crack, and then you make the rock weaker, and when you impact, you break it easier.
Hi, Mark. I have two questions. One is, are there conditions that are optimized for thermal cracking? I mean, are there specific asteroid conditions, whether it's, I mean, certainly heliocentric distance, it sounds like rotation rate, thermal inertia, whatever, that you'd look at to see the effects maximized?
We haven't done an extensive study of these, so we have a, we'll do it. We'll do it, and we'll give you an answer. But we will, for sure. For example, how do you say, metallic meteorite, for example, meteoroid would experience very, very small thermal cracking, if any, for example. And this, for example, this